today we're going to be reviewing an example problem about how to graph velocity versus time, and then how to find our acceleration, and then also our distance that the object has traveled per second. Okay, so if I'm looking at the questions, here is the scenario. Using a motion detector, the following data was collected for cars rolling down an incline. Data was collected below. So your graph should be a 15 by 15 grid. So what that means is a piece of graph paper just cut out with 15 squares by 15 squares. For each of the following data sets, we're going to graph, we're going to graph the velocity versus time graph, calculate the acceleration of the car with units, and then write a data table for the position of the car as a function of time, distance and time, and we're going to pay close attention to our starting velocity, and we're going to use this equation in order to fill out this box. So let's take a look at number one. The first thing I'm going to do is graph. So number one, part A is graphing. I have my time in seconds as my x variable and my velocity in meters per second as y, and all I'm going to do is take a look at number one, and I'm going to graph this data right here. So I'm going to pick a scale that best fits my data. So remember, your scale is not your data, it's the one that best fits your data. Okay, so let's start with time. So 0 to 5, I want to use my entire graph paper here. So I have time 0, and then 1, 2, 3, this will be 1, 1, 2, 3, 2, 1, 2, 3, 3, 1, 2, 3, 4, 1, 2, 3, 5. So my scale is even, it makes sense, and I'm using my entire graph paper. So now I'm going to do the same thing, but on this side, I know I'm starting at 0 and I'm ending at 15, so I'm at 0 again. I know I've got a 15 by 15 grid, so 15 will be at the top. So every single line is 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? So now I'm going to graph. 0 and 0 is my first data point because the object has a 0 velocity, 0 meters per second velocity at time 0. At 1 second, I'm at 3, 1, 2, 3. 2 seconds, I'm at 6 meters per second, so 1, 2, 3, 4, 5, 6. 3 is 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. At 4 seconds, I'm at 12 meters per second, so let's see, 9, 10, 11, 12. And then lastly, at 5 seconds, I'm at 15 meters per second, which is going to be up here at the top corner. So this, those are my data points for my scenario. So I'm going to use a ruler and I'm going to connect them. All right, so there it is. So now what this shape of this curve tells me is that this is a constant acceleration because my line is increasing. It is positive, so it's increasing in terms of velocity per second, and then it is also constant because the line is not exponential. So that was part A. So part B now, calculate the acceleration of the car. So B, what I'm going to do over here is I know that my acceleration is my final velocity minus my initial over my final time minus my initial. This is also finding the slope of a line, so you could say delta y over delta x. So I'm just going to pick data points from the table to do this. I always like to pick the 0 because that's the kind of one of the easier ones to solve. So I'm going to say A. I'm going to pick the first 2 sets. So my final, well, let's just do the last one. So 15, I'm going to say 15 meters per second minus 0 meters per second divided by my final time, which is 5 seconds minus 0 seconds. So all I'm doing is picking my first and my last data points to then put them into this equation so I can solve for my acceleration. This is also the slope of this line. So I end up with 15 meters per second over 5 seconds. So 15 divided by 5 is 3 meters per second squared. So the note that the acceleration is seconds squared. So that's part B, which is solving the acceleration of the car. Okay, so from here is kind of the trickier part when we get to part C, because now I want to know position. So what is my actual position of the car as a function of time for all of these 5 seconds? Meaning, how far has the car actually traveled? Okay, so for part C, I'm just going to list out my variables for this equation. So I'm just doing number 1 right now. So my distance, or my position, is what I'm solving for. My initial velocity, so this V0, V0 means initial velocity, or what you're starting with. And in my data table, it's 0. Note for number 2 and number 3, it is a different data table, or different starting velocity rather. My time, I'm going to use all of my data points. So 0 seconds, 1 second, 2 seconds, 3, 4, and 5 when I'm doing my data table. My acceleration is what I just solved for, 3 meters per second squared. Okay, and my equation that I'm using is my distance, or my position, is my initial velocity times time plus 1/2 my acceleration times time squared. Okay, so now I'm going to set up a table that I can use to start solving. Okay, so I'm going to use the rest of my paper here to make it really nice and big and neat. So my time in seconds and my position in meters. All right. Ooh. So starting with time at 0 seconds. So when my time is 0 seconds, we're going to plug this in and we're going to see how far our car has traveled. Now I'm sure you could guess, but we're going to plug it all in so we can get in the habit of plugging it into this equation. So my distance equals my V0. So up here I've already labeled that that's 0 meters per second times my time of 0 seconds in this first data point plus 1/2 times my acceleration, which is 3 meters per second squared, times my time, which is 0 seconds squared. Okay, now 0 times 0 is 0. 0 times 3 times 1/2 is 0. So we know that the car has gone 0 meters in this first 0 seconds. Okay, now again, I'm sure we could have guessed that, and we know by looking at the graph what that means, but we are saying that for this time 0 to get in the habit of solving this equation. Okay, so now let's do time is 1 second. So instead of 0 seconds, I'm now 1 second. So we're going to plug it into the same equation again. Distance equals my V0, which is 0 meters per second, because I'm starting from rest, times 1 second plus 1/2. 3 meters per second squared is my acceleration. I'm just following this equation right here, times my time, which is 1 second squared. Okay, 0 times 1 is 0. Seconds and seconds cancel. So 0 meters plus 1/2 of 3 times 1 second squared. Well, 1 second squared is 1. So then 1/2 of 3 is 1.5 meters. And my second squared and my second squared cancel. So 0 plus 1.5 equals 1.5 meters. So in the first second, this car has traveled 1.5 meters with an acceleration of 3 meters per second squared. So we're just going to repeat this for each second in our data table. So t equals 2 seconds. Here we go. Distance equals my V0, which is still 0 meters per second, times 2 seconds now, plus 1/2, 3 meters per second squared, 1/2 acceleration, times t squared, which is 2. So again, 0 times 2 is 0 meters. Seconds and seconds cancel, plus 1/2, 3, 1.5, times 2 squared, which is 4. Your seconds and your seconds canceled. So you can even put this in your calculator, but you would end up with 6 meters. So 0 plus 6 meters is 6 meters. So now we can really see that we're accelerating because our distance is increasing so much. So in 2 seconds, this object going 3 meters per second squared as an acceleration has now traveled 6 meters. Okay, so let's do it again for 3 seconds, and we're just going to keep following the same equation to fill this table in. So distance equals 0 meters per second, because that's my starting velocity, times 3 seconds plus 1/2, 3 meters per second squared, times 3 seconds squared. Okay, so again, 0 times 3 is 0 meters, seconds and seconds cancel, plus 1/2 of 3 times 3 squared. So 1/2 times 3 times 9 gives us 13.5 meters. Second squared cancel. So 0 plus 13.5 is 13.5 meters. So you can see with the distances that we are increasing. T equals 4 seconds. We're almost done. We just have 4 and 5 seconds left. Again, our starting velocity is 0 times 4 seconds. I'm just plugging it into this equation for each second that the car has traveled. 3 meters per second squared, 4 seconds squared. Again, 0 times 4 is 0, plus 1/2 of 3 times 4 squared, which is 16. So this is 24 meters when you calculate this out. So 0 plus 24 is 24 meters. And lastly, let's do t equals 5 seconds. Distance equals 0 meters per second times 5 seconds. Again, initial velocity times my time, plus 1/2 of my acceleration, 3 meters per second squared, which I got from the graph and my data points, times 5 seconds squared. So 0 times 5 is 0, plus 1/2 times 3 times 5 squared, which is 25, is 37.5 meters. So after 5 seconds, my car would have traveled 37.5 meters. Okay, so this is how we're going to be graphing acceleration. First with the actual graph, using the graph and the data points to find the acceleration, and then plugging that into this equation to solve for position at every second. Now for us, it was 0 for this first value every time because our initial value of our velocity was 0. But that's not going to be the case for the other 2 examples. So pay attention to what your initial velocity is at time 0. And that's what we're going to do for the next 2 problems. Set it up just like this, use the whole page and make it neat, and be sure to show all of your units every time.